Welcome back. We've defined smooth functions and strongly convex functions, and it's time to derive some of their properties that are going to be directly useful for us in coming up with guarantees, rates of convergence for using gradient descent. So let's just remember what the basic definitions are that we're working with. A function is convex if f of y is lower bounded by a linear approximation. This is our basic definition of convexity that holds whether we're differentiable, as is the case for a smooth function, or whether we have to work with a subgradient, an element of the subdifferential. And we saw that if f is beta smooth, this means that its gradient is Lipschitz. Again, this means that the gradient of f of y compared to the gradient of f of x is not very big when y and x are close. Specifically, this is upper bounded by beta times y minus x. And we saw that a consequence of this is that we can find an upper bound, a quadratic upper bound, on any smooth function. F of y is now upper bounded, opposite sign from our standard definition of convexity, by a quadratic function, f of x plus gradient of f of x y minus x plus beta over 2 times y minus x squared. Again, note that this upper bound actually touches the function at the point y equals x. So it touches it at the point of approximation. And that's why something like the absolute value function at 0 cannot be upper bounded in this way by a quadratic. So we're going to use this property to derive this relationship, to derive several very important properties of smooth functions. Now remember our example of our polynomial. And what did we see? We saw that every single step of gradient descent actually made the function value better, smaller. So gradient descent always strictly improved our optimal solution. And this is something that does not have to be the case in the absence of smoothness. And we gave an example of that. And in particular, we gave an example where this is not the case even if you take a tiny, tiny, tiny step size. So it's not just a question of step size, because even for smooth functions, and if you take a huge step size, you could make your life worse. So let's see how this fact that gradient descent guarantees strict improvement for a smooth function, how that follows from our quadratic upper bound. Again, just repeating from the previous slide, we have that f of y is less than or equal to f of x plus the gradient of f of x times y minus x plus beta over 2 times y minus x squared. What does gradient descent do? The gradient descent algorithm tells me that my update, x plus, is equal to x minus a step size times my gradient. So let's see what is the value of f of x plus. What I want to show is that this is going to be strictly less than f of x unless we're already at the optimal solution. In which case you can see that the optimal solution is just a fixed point of the gradient descent iteration. And you can see that this quadratic upper bound that I have is exactly the tool that I need if I'm hoping to get an upper bound on f of x plus. So plugging in above, I get that f of x plus is less than or equal to f of x plus gradient of f of x. Y is my x plus, so this is x plus minus x plus beta over 2 times y minus x. Again, y is x plus minus x. Now what is this x plus minus x? Just looking at my iteration, x plus minus x is equal to minus eta times the gradient of f of x. Plugging that back in, I find that f of x plus is upper bounded by f of x plus minus eta gradient of f of x gradient of f of x. I just brought the minus eta outside of the dot product. Plus beta over 2 times the squared norm of x plus minus x. Minus eta comes outside squared as a positive eta squared, and I have gradient of f of x squared. Simplifying, this tells me that f of x minus eta times the gradient of f of x squared plus beta over 2 eta squared times the gradient of f of x squared. This is this upper bound. I can group the last two terms. So this is equal to f of x minus, let me take out the eta, which is a common to both, and I have 1 minus eta times beta over 2 times the gradient of f of x squared. We're close. This tells me that if I choose eta small enough, then I'm subtracting something strictly positive. So we know that this term is positive, unless x is equal to x star, in which case it's equal to 0. Otherwise, it has to be strictly positive. And what about this term? As long as this is positive, then I know that f of x plus is strictly less than f of x. And I can make this strictly positive by choosing eta small enough. So if I choose eta small enough, so in particular, if I choose eta less than 2 over beta, then this term is going to be strictly positive. So then eta times 1 minus eta times beta over 2 will be strictly positive, and therefore this shows that we have a strict descent algorithm. So typically, we choose eta equal to 1 over beta. It's less than 2 over beta, but also it's what we get when we optimize this term. And if we choose eta equals 1 over beta in gradient descent, then I have that x plus is equal to x minus 1 over beta times the gradient of f of x, and f of x plus is less than or equal to f of x, and let's see what we get. I get 1 over beta here. Let's do this calculation. So in this case, eta times 1 minus eta beta over 2 is equal to 1 over beta times 1 minus 1/2. Or in other words, 1 over 2 beta. So f of x plus is less than or equal to f of x minus 1 over 2 beta times the norm of f of x squared. This shows that gradient descent is in fact a descent algorithm, and we can call it that in the future. There's some other properties that a function satisfies if it's smooth, and these are going to be useful for us in the future. Again, if f is beta smooth, then 1 over 2 beta times the gradient of f of x is less than or equal to f of x minus f of x star. And this is upper bounded by beta over 2 times x minus x star. And that should be clear here that x star is the solution to the unconstrained minimization problem. Minimize f of x without constraints. So let's see where these come from. Not surprisingly, we're going to use the main tool that we're going to have at our disposal whenever f of x is smooth, and that's the quadratic upper bound. So again, we use the quadratic upper bound, which is f of y is less than or equal to f of x plus the gradient of f of x times y minus x plus beta over 2 times y minus x squared. In fact, we can see that term b we get immediately from this quadratic upper bound. So for b, let's use our quadratic upper bound. How are we going to use it? Well, we need an upper bound on f of x minus f of x star. So we're going to apply this quadratic upper bound with y equals x and x equals x star. So let me, since we'll be referring to this all the time, let's call it star. So from star, we get that f of x is less than or equal to f of x star plus the gradient of f of x star times x minus x star plus beta over 2 times x minus x star, direct application. This term equals 0 because it's the gradient at the optimal solution. And you can see I immediately get b. So this implies that f of x minus f of x star is less than or equal to beta over 2 times x minus x star, which is exactly what we needed. For a, no surprise, we're again going to use this quadratic upper bound. It takes a little bit of extra thought here on how to use it. So note that f of x star is less than or equal to f of y. By definition, f of x star is the optimal solution. So it's less than or equal to f of y for any y. And f of y, in turn, is upper bounded by this quadratic approximation, by this quadratic upper bound. So if f of x star is less than or equal to f of y, and f of y is less than this quadratic approximation, then I can just minimize the right-hand side. Minimize the quadratic upper bound over y. So if I minimize over y, how do I do that? Again, it's just a quadratic. Take the gradient, set it equal to 0. What value am I going to find? So if I take the gradient here, I'll find that the gradient of f of x, so we find that the gradient of f of x, that's the gradient of the first two terms with respect to y, 0 plus gradient of f of x, plus beta over 2 times y minus x equals 0. So in other words, the y that I want to plug in that minimizes this right-hand side is equal to y is equal to x minus 2 over beta times the gradient of f of x. And if you plug this value in, I plug in this value of y, I find exactly this lower bound. So I find that f of x minus f of x star, I'm going to move f of x star over to the right-hand side and move everything else that has a y in it over to the left. And I'm going to find that this is exactly equal to 1 over 2 beta times the gradient of f of x squared, which is exactly what I needed for this first inequality. Another property that's going to be useful, and that's going to be useful a little bit later, but since we're deriving properties of smooth functions, it makes sense to do this now, is called co-coercivity. So co-coercivity is actually a more general function of operators here, but we're going to just prove it for the gradient of a smooth function. If f is a beta smooth convex function, then its gradient satisfies gradient of f of x minus gradient of f of y, dot product with x minus y. This is an object that we've seen many times by now. So we know that for convexity, this is greater than or equal to 0. In fact, the non-negativity of this is called monotonicity. If this is non-negative, we say that f is monotone, and we've showed that f being monotone is equivalent to f being convex. So we know this is greater than or equal to 0, but in fact, if f is smooth, we get a slight strengthening of this. This is greater than or equal to 1 over beta times the gradient of f of x minus the gradient of f of y squared. We know it's greater than or equal to 0, but this is a little bit, this is a strengthening of this. So let's show this. So to show this, this is what we're going to do. Look at the function f sub x of z that I'm defining as f of z minus the gradient of f of x with z. So what do we know about this? Well, note that the optimal solution is z equals x if I want to minimize this function. Z star equals x is minimizer of fx of z. How can you see that? Just take the gradient of the right-hand side with respect to z, and what do you get? Gradient of f of z minus gradient of f of x. And setting that equal to 0, you'll see that if I set z equal to x, I get 0. So this is a minimizer of f of x. Again, perhaps there's more than one minimizer, but that's certainly a minimizer of f of x. And similarly, let me define fy of z to equal f of z minus gradient of f of y times z. And for the exact same reasoning, z star equals y is a minimizer of fy of z. How are we going to use these two functions? F of y minus f of x plus gradient of f of x, y minus x. This is generically greater than or equal to 0 for a convex function. And in this case, I can express this in terms of fx of z. So again, just to see that, let me write this out as f of y, let me group it a little differently, f of y minus gradient of f of x with y, first term, minus f of x minus gradient of f of x with x. So note that this is exactly fx of y, and this is exactly fx of x, looking back at how I've defined this function. Okay, so what do we have here? So let me just write that again. So this is equal to fx of y minus fx of x. But we just said that if I evaluate fx at x, this is the minimizer. So looking back at what we just showed, let me flip back a slide to show you what property of smooth functions we're going to use. We're going to use property A here, which says that f evaluated at a point minus f evaluated at its minimizer is bounded below by 1 over 2 beta times its gradient. So applying it here, applying this exact same thing here, I find that this is greater than or equal to 1 over 2 beta times the gradient of fx of y. Now you should think for yourself for a second, how did I apply this inequality? It's f that's beta smooth. And I need beta smoothness in order to make sure that this inequality holds. So it's f that's beta smooth. We didn't say anything about fx. But looking at fx and fy, these are just equal to f minus a linear term. And adding a linear term, subtracting a linear term, these cannot change any kind of curvature properties, or convexity for that matter. So if f is beta smooth, or for that matter, if f is strongly convex, then f plus or minus any linear function is again going to be beta smooth. So I can again apply that result that we derived in the previous slide to the functions fx and fy. And now plugging in what the gradient of fx is, I find that this is equal to gradient of f of y minus gradient of f of x, just by definition. Okay, so we're not quite there yet, but we're getting there. So I have derived that f of y minus f of x plus gradient of f of x times y minus x, that's this term, is lower bounded by this. But now I can just I can flip the roles of y and x and also get, so similarly, by flipping the roles of x and y, I can find that f of x minus f of y plus the gradient of f of y times x minus y. You see what I've done is I took this term here, and I just flipped wherever I had x, I wrote y, wherever I had y, I wrote x. This is lower bounded by 1 over 2 beta times, again, the same thing. I don't even have to flip y and x here because I have the norm. And if we add these two terms, what's going to happen? The f of x and f of y are going to cancel because they have opposite signs, and I'll have exactly the relationship I need for co-coercivity. So let me call this A, let me call this B. Adding A and B gives me co-coercivity. Again, this is a technical property. It's a more general concept that's important to generally be aware of, but we're going to see it come back when we prove the convergence rate of gradient descent for smooth and strongly convex functions. Okay, a few more comments on strong convexity. So remember that our definition of strong convexity, f is alpha strongly convex if f of x minus alpha over 2 times x squared is convex. And now applying just the standard convex inequality, the fact that a linear approximation lower bounds a convex function, to this, we found that strong convexity is equivalent to a quadratic lower bound. F of y is greater than or equal to f of x plus the gradient of f of x times y minus x. Again, this is our standard bound that any convex function satisfies. But strongly convex functions also satisfy something stronger, which is that we have this quadratic here on the right-hand side. Okay, so this is the key property that we want to use for strong convexity. And very similarly to what we had for smooth functions, we have if f is alpha strongly convex, then we have alpha over 2 times x minus x star, where x star is the minimizer of f of x, the global minimizer, is less than f of x minus f of x star, which is less than or equal to beta over 2 times x minus x star. Very similar, whoops, times the gradient of f of x squared. Very similar, if you look back to the analogous slide for smooth functions, it looked very similar, but with the right and left-hand sides flipped. So how do we get this? For both, we're going to use our quadratic upper bound. Call this property A. Call this property B. Sorry, I've made a. This should be 1 over 2 alpha. For both A and B, we use the quadratic upper bound. Again, just to copy this from the previous slide, this says that f of y is greater than or equal to f of x plus the gradient of f of x times y minus x plus alpha over 2 y minus x squared. If we plug in x is equal to x star and y is equal to x, we get f of x is greater than or equal to f of x star plus the gradient of f of x star, as always this is 0, plus alpha over 2 x minus x star. This is equal to 0, which gives us inequality A. F of x minus f of x star is greater than or equal to alpha over 2 times x minus x star. For B, we're going to do the same thing that we did before. If I have a quadratic lower bound, then certainly f of x star is also going to be greater than or equal to any single value of that quadratic, because that quadratic sits below my entire function f. If f of x star is greater than any value of that quadratic lower bound, then it's certainly, f of x star is going to be, sorry, let me back up. F of x star is not going to be lower than any value of that quadratic upper bound, but it will certainly be less than or equal, it will be greater than or equal to the minimizer of the quadratic lower bound. And so I have a quadratic lower bound in my function. Right? It lies below all of my function. That means that the lowest point of the quadratic lower bound better be lower than the lowest point of my function. Otherwise, it couldn't possibly always be underneath it. So this is going to be greater than or equal to the min over y of my quadratic lower bound. F of x plus gradient of f of x times y minus x plus alpha over 2 y minus x. You see, we have a way of reducing problems to very simple ones, minimizing a linear function, minimizing a quadratic function. We just do this again and again. Now we're in a position where we need to minimize this quadratic lower bound. We know how to minimize a quadratic, except take the derivative, set it equal to 0. We take the derivative, or the gradient, set to 0. What do we find? Take the gradient with respect to y, right? And we find that gradient of f of x plus alpha over 2 times y minus x equals 0, or the y that I want is equal to x minus 2 over alpha times the gradient of f of x. If we plug in this value for y, we find that f of x minus f of x star is less than or equal to 1 over 2 alpha times the gradient of f of x. So plug this back in to here, and I have that f of x star is greater than or equal to this value. I'm going to bring f of x over to the right, bring everything over to the left, and I'll have f of x minus f of x star is less than or equal to the only term that survives on the right-hand side. And finally, we want to prove a similar property as we did for smooth functions called coercivity, not co-coercivity. So if f is alpha strongly convex, then gradient of f of x minus gradient of f of y times x minus y. We know this is greater than 0 just by convexity, but something stronger holds. It's greater than alpha times x minus y squared. How does this follow? Simply directly from the definition of of strong convexity. So recall, f is alpha strongly convex if the function g of x minus alpha over 2 times x squared is convex. Well, if this function is convex, then it's monotone, its gradient is monotone. So I got a little bit ahead of myself here. If g of x, which is equal to f of x. G of x convex is equivalent to g of x, the gradient of g of x being monotone, which is saying that the gradient of g of x minus the gradient of g of y times x minus y is greater than or equal to 0. And plugging in what this means, this gives us exactly the property that we want. Gradient of g of x is the gradient of f of x minus alpha times x. Gradient of g of y is the gradient of f of y minus alpha times y. And grouping these terms, we find that this immediately implies, that non-negativity of this immediately implies that the gradient of f of x minus the gradient of f of y times x minus y is greater than or equal to alpha times x minus y squared. A little bit easier than co-coercivity, but also something that's going to be a useful property. So next time, we're going to use these properties in order to derive rates of convergence for gradient descent, and we'll pick it up then.